Okay guys, welcome to lecture number 6. We're going to talk today about Riemann sums and some properties of definite integrals. So before we get to the Riemann sum part, I want to kind of give you some basic properties of definite integrals. And before we go any further, a definite integral, as you learned in pre-cal, is the area under a curve between the curve and the x-axis and in between two x values. Okay, so if I draw a function here, I just want to show you a couple of properties, and I'm going to try to do that using a picture. So let's say that we have the two x values a and b, and then we have some function that goes from a to b. Okay, well let's say that I wanted to find the area in this first property, the area, the integral I should say, from a to a of f of x. Well, if I just try to find the area from a to a, I haven't really gone anywhere on the x-axis, and so I haven't accumulated any area if I just travel on the x-axis from point A to point A. So because of that, anytime we have an integral that have the same bounds as the lower bound and the upper bound, the answer is automatically going to be 0. So that's the first thing that you should know, is that anytime the bounds are the same, we just say that the integral is equal to 0. Okay, the second property is kind of what's called an additive property of definite integrals. And so what that basically means is that if I put a point in between a and b on here and call it c, then basically what we have is we have the area from a to c, which is right here, plus the area from c to b, which is right here, is really just equal to the entire area from a to b. So the way that we'll write that as a property is the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And so this one is represented by the blue up there, and the second term in this addition is represented by the red area up there. And so I can split that into two integrals by taking some point in the middle of a and b. Okay, and then the final property that I want to show you is a way that we can switch the bounds if necessary. And so basically, this area is what's called a signed area. Okay, meaning it is either positive or negative. And I know you've grown up thinking that area is always positive. And in some cases, that's true. But when we talk about definite integrals can be negative. And so basically, what happens is that if we integrate from left to right, so for instance, from A to B, we consider that to be positive area as long as it's above the axis. And right now we're just kind of talking about positive functions only. And so if I integrate from left to right, that is a positive area. But if I integrate from right to left or backwards, that is considered to be a negative area, again, as long as you're talking about a function that is above the x-axis. So because of that, our final property, if we want to switch the bounds of integration to instead say the integral from b to a of f of x dx, then what we need to do is we need to put a negative sign in the front. Okay, so I believe you have a couple of problems on your assignment that will utilize these properties, so I want to see if you can figure those out given the properties. Okay, well, what if I want to find the area under a function that's not a nice geometric figure? Okay, so in pre-cal, you learned how to find a definite integral as long as the function was a really nice geometric figure. For instance, a circle or a triangle or a rectangle or something like that. Well, this is where the idea of a Riemann sum comes into play, and I'll illustrate that here using an increasing function. Okay, so if I have an increasing function here, then what I want to do in order to find the area under that curve is I want to split this interval from a to b. I'm going to consider this to be b. I want to split it into subintervals. And so I'm just going to take points here on the x-axis that are in between a and b. And however many that I take will depend on how good the approximation to the area is. And we'll talk more about that a little bit later. So there's a couple of choices here if I want to use a rectangle. The first is to use the left endpoint from any subinterval. Oops, sorry about that. The left endpoint. So if I choose the left endpoint in this first subinterval, then that's really not going to create a rectangle at all. From the next subinterval, I'm going to choose the left endpoint, and I'm going to make a rectangle. From the next subinterval, I'm going to again choose the left endpoint up there on the function, and that's going to create a rectangle. And then in the next subinterval, the left endpoint. Okay, and then from the last subinterval, the left endpoint. Okay, so what I have here is these areas of the rectangle that help me approximate the area underneath the curve. Now, what you should hopefully notice is that by using the left endpoint, so this is where we use the left endpoint, we didn't capture all of the area. And so that leads us to filling in the first blank here. If a function is increasing, then a left Riemann sum is going to under-approximate the area under the curve or the definite integral. Okay, if I instead take the right endpoint from every subinterval, so I'm going to try to draw the same figure here, increasing function. Here's B, here's A. I'm going to try to take the same number of subintervals if I can. And now this time I'm going to take the right endpoint. So from A to this first tick mark, I'm going to take the tick mark and make a rectangle there, like that. Then I'm going to have a rectangle here, come down and across to make my rectangle. Then I'm going to go up to the function and over for a rectangle, up to the function, over for a rectangle, and then up and over to create my rectangle. And now hopefully what you're noticing, I'll use a different color here, now you should be noticing that we are over-approximating the area under the curve. Okay, so what that means is that if a function is increasing, and notice that both of these functions were increasing in my picture, then a right Riemann sum will over-approximate the exact value of the integral or the area under the curve. Okay, well, what if the function is decreasing? Do you think it's going to be the same? Okay, well, if you answered no, then you're correct. So if I have a decreasing function, okay, so let's draw a decreasing function here. And let's first of all use the left endpoint of every subinterval. So here are my subintervals. I'm not creating a lot of subintervals, but just enough to kind of illustrate the point here. So I'll use green again for our left Riemann sum. Then I'm going to take the left endpoint. So the left endpoint of the first subinterval is going to be there. The left endpoint for that subinterval is there. The left endpoint here is there. And then here to here. And so hopefully what you notice is that, again, I am over-approximating the area under my black curve. Okay, so if a function is decreasing, then the left Riemann sum will over-approximate the area under the curve. Okay, similarly, if I draw a decreasing function and then use the right endpoints to create my rectangles, then this is going to be, as you're about to see, an under-approximation. So let's again use the same color. We're going to use the right endpoint here. Okay, so you can see there's an under-approximation, there's an under-approximation. Try to get it as close as I can. And so this area in pink is not enough to be the entire area under the curve, and so this is an under-approximation. So it'll under-approximate the area under the curve. Okay, so you do need to have this memorized. I had a student a couple of years ago come up with a good acronym to kind of help us out, and that acronym is I love you, Drew. And so what that means is kind of goofy, but it helps. It means increasing, so this stands for increasing left is an under approximation, and decreasing right is also an under. And so you can fill in the blanks for the other two cases. So if you can remember I love you Drew, you can determine is it an over approximation or is it an under approximation. Okay, so the following examples illustrate how to use a Riemann sum to approximate definite integrals, and I'm also going to introduce to you a meaning of the definite integral in a particular case. Okay, so if you remember back to our first couple of lectures, we talked about the interpretation of the derivative was instantaneous rate of change. And so if you had an amount and you took the derivative of a function that represented the amount of something, you got the rate of change in that amount at a particular time. If we go backwards from that idea, so if f prime of x is the rate of change of a quantity f, then the definite integral of f prime from a to b gives the total change in that amount, or just the amount. Okay, so that's what you need to really recognize here, and this is something that I keep doing that on accident. This right here is what you need to have in your knowledge bank as you come into class. Whenever you integrate a rate, you get an amount. So if you need an amount and you're given a rate, you're going to integrate to get that amount. Okay, so let me illustrate how we're going to use a right Riemann sum in this problem. This is talking about the volume of a spherical hot air balloon expands as the air inside the balloon is heated, and the table is giving us selected values of the rate of change of the radius of the balloon. Okay, so that's very important that you understand we are given a rate of change in this problem. Okay, so it says to use a right Riemann sum with 5 subintervals indicated by the data in the table to approximate that integral. So what I'm going to do is I'm going to rewrite down the integral. So the integral from 0 to 12 of r prime of t dt. And then this is an approximation, so I'm going to draw an approximation symbol, not an equal symbol. Okay, so for a right Riemann sum, here's what we do. We take a look at our first subinterval. So our first subinterval is here between the time values 0 and 2. Since this is a right Riemann sum, we're going to take the right-hand y value as the number that we want. So the right-hand y value here is 4.0. And then because it's a rectangle, we have to multiply by the width. Well, the width in this subinterval is from 0 to 2, okay, which means that the width is going to be 2. Plus, now I go to the next rectangle on the next subinterval. So the next subinterval is here from 2 to 5. Well, again, I'm doing a right Riemann sum, so I'm going to take the right-hand number in that subinterval, which is the 2.0. So I'm going to write that down, 2.0, and then multiplied by the width of that subinterval, and the width of that subinterval is 3, since the subinterval went from 2 to 5. So it's basically just the difference in the t values. Plus, go to the next one. Again, I'm going to take the right-hand value from that subinterval, so that's going to be 1.2, multiplied by the width, which if I look at the difference in the t values is going to be 2. Plus, go to the next subinterval, 1.2 to 0.6. We're going to take the 0.6 since we're doing a right Riemann sum, and then multiply by the width, which is from 7 to 11, which gives me 4. And then finally, we're going to use the last subinterval. We're going to take the right-hand value there, which is 0.5, multiply by the width, which in this case is 1. Okay, and just for time's sake, I went ahead and did the arithmetic there. It's 19.3. Now, using correct units to explain the meaning of this integral in terms of the radius of the balloon. So again, we are integrating a rate of change. Anytime we integrate a rate of change, it gives us the change in the amount of that quantity. And so this integral, and I'm going to rewrite it down here so I can explain what it means. Since we are integrating a rate of change, this is the change in the radius. Okay, and it does say to use correct units, so I need to look back up and see what would my radius be measured in. Well, since the rate of change was measured in feet per minute, my radius is going to be measured in feet. And then the last thing that I need to talk about are the bounds of integration. So the bounds of integration were from 0 to 12, and so I need to say from t equals 0 to t equals to 12, and time in this problem was measured in minutes. Okay, so that is a way to figure out what the meaning of that definite integral is, and you're going to have to get used to doing this kind of thing in class, justifying your answer and explaining the meaning of your answer as well. Okay, is your approximation greater than or less than the actual value of the integral? So this right here, they're talking about the actual value of the integral. They want us to say, is this an approximation greater than or less than? Well, if you notice, our function up here, r prime of t, is decreasing. And since we used a right Riemann sum, a decreasing right Riemann sum is always an under approximation. If you think back to your acronym, I love you, Drew, if we have a decreasing function with a right Riemann sum, that's going to be an under approximation. Okay, so we're going to write our answer, and we are going to say this is an under approximation. And the reason for that is because r prime of t is decreasing. And not only that, we used a right Riemann sum. So we used a right Riemann sum. Okay, so those are the two reasons that you have to state for whether or not something is an under approximation or an over approximation. And this acronym right here is incredibly helpful, so make sure you don't forget that. Okay, example 2, we want to now do a left Riemann sum, but before we do that, it says to use correct units and interpret the meaning of this definite integral in the context of the problem. Well, v of t is given as a velocity. It says back up here that Ben's velocity is given by v of t. So v of t is a velocity. So if I have absolute value of velocity, remember that absolute value just makes everything positive. Velocity is a quantity that can have either positive or negative values. Positive values would mean that you're traveling in the positive direction, and negative values would mean you're traveling in the negative direction. But if I take off the direction part and only care about the magnitude or the value, then really what we're talking about is speed. Okay, so that's something that you'll need to know in class also, is that the absolute value of velocity is the speed. And so basically what happens is whenever we integrate speed, we're getting the total distance traveled by whatever particle or person that we're talking about. Okay, so what you need to know is that this integral is talking about total distance traveled. And in this particular problem, we're talking about a person, Ben, who's riding his unicycle back and forth along a straight east-west track. So what we're going to say is that the integral from 0 to 60 of the absolute value of the velocity, dt, is the total distance Ben rides his unicycle. I apologize for the bad handwriting here and also the bad spelling. Let me see if I can spell unicycle, U-N-I-C-Y-C-L-E. There we go. And then I need to think about what is my distance going to be measured in. Well, it's not going to be measured in meters per second. It's going to be measured in meters. So we're going to say in meters from, again, I have to say something about the time. T equals to 0 to t equals to 60 seconds. Okay, so that is what I have to have in my answer in order to get full credit. Okay, second part of the problem says to approximate the integral from 0 to 60 of the speed using a left Riemann sum this time with subintervals indicated by the data. Now, because we're integrating velocity, this b of t right here doesn't really matter. It probably mattered for another part of this question. This is a released FRQ. So you're not going to use that on this particular part, so I'm just going to scratch it out just to make sure that we don't accidentally use a number from that row. Okay, so the integral from 0 to 60 of the absolute value of velocity dt is approximately, using a left Riemann sum. Well, if I look at the first subinterval, what I'm going to use this time is the left endpoint. So the left endpoint there is going to be the one that's on the left. That would be the 2.0. And then again, I'm going to multiply by the width of that subinterval, which goes from 0 to 10, giving me a width of 10. Plus, go to the next subinterval. That would be 2.3 and 2.5. We're going to use the one on the left since we're doing a left Riemann sum, and then multiply by the width of that subinterval, which is 30, since that subinterval goes from 10 to 40. Plus, the last subinterval we're going to use 2.5, multiplied by the width of that subinterval, which is going to be 20. Okay, and if you do the arithmetic there, that's going to equal 139 meters. Okay, so that's a left Riemann sum. We did a right Riemann sum in example 1, so if you have any questions on either of those, then please let me know. Okay, example 3, we're talking about train A, which goes back and forth on an east-west section of railroad track. Its velocity is given in this table. So you guys saw this table in a previous lecture, and now we're doing another part of that released FRQ. Okay, so it says at time t equals to 2, train A's position is 300 meters east of the origin station. We are going to have to use that information at some point, so keep that in mind. That's why I highlighted it. And the train is moving to the east. Write an expression involving an integral that gives the position of train A in meters from origin station at time t equals to 12. So let's go ahead and do that first. So usually the way that we denote position is with the variable s. So I'm going to call it s sub a of t. And if I want to figure out what my position is, the first thing I have to say is where am I initially? So at t equals to 2, it tells me that I am 300 meters east of origin station. And so that is my initial position, 300. Then I have to say, okay, well, where have I gone? Well, I have gone from t equals to 2 up to t, because I don't know what t is, of v sub a of t dt. Okay, so that is my position of train A at any time t. It then says to use a trapezoidal sum with 3 subintervals to find the position at time t equals to 12. Sorry about the announcement here. Good old Miss Henry telling us to clock in. Yes, I already clocked in and we're ready to go here.
If you see somebody come in late, please remind them to clock in, because I will not be able to go by and correct that. Mr. Morris, I need you in the front office, or if you'll call me and tell me where you are. Thank you.
Okay, so sorry about that. Hopefully that doesn't happen again as I try to get these videos done for your summer assignment. So use a trapezoidal sum to determine the position at time 12. So S, whoops, let's use the marker here. S sub A of 12. Okay, what I'm going to do is just plug in 12 for t into my formula here. So this is going to be the integral from 2 to 12 of v sub A of t dt. And so what they're wanting us to do is to use a trapezoidal sum in order to determine the approximation for this integral right here, okay? So here's how we're going to do a trapezoidal sum. If you remember the area of a trapezoid, the area of a trapezoid is 1/2 multiplied by the bases added together multiplied by the height. Okay, well the height in this case is just going to be the width of the subinterval. So you could call that delta t if you wanted to, the change in the time. Okay, so that's really what the h is going to represent. The B1 and the B2 are just going to represent the y values. So the y values, of course, are in this column. And so what I'm going to basically do is be adding those together, dividing by 2, and then multiplying by the width of the subinterval. Okay, so what we do when we do trapezoidal sums is we basically just put the 1/2 out at the front, because I know I'm going to be using that for every term, because that comes from the formula back up here for area of a trapezoid right there. Okay, so I factor out the 1/2. I then go to the first subinterval. I have 0 and 100 as my y value. Since I'm doing a trapezoidal sum, I'm going to add those together, which is going to give me 100, and then multiply by the width of the subinterval, which is 2. Plus, go to the next subinterval. I'm going to add those y values together. 100 plus 40 is 140, multiplied by delta t, and delta t in this case is going to be 3. I'm going to come down here since I'm kind of out of room. Plus, I'm going to add 40 and negative 120. That's going to give me negative 80. And then multiply by the width of the subinterval, which is going to be 3. Plus, add the y values in this subinterval, which is going to give me negative 270, multiplied by delta t, which is 4. And that is going to give me my position at time t equals to 12 using a trapezoidal sum. So if you put the calculator to that, you're going to get negative 150 meters. And so basically what that means is that train A is now to the west of origin station at time t equals to 12. Okay, example 4, hot water is dripping through a coffee maker. This function c of t represents the amount of coffee in the cup at time t. Okay, so it says to use a midpoint Riemann sum. So we're now going to illustrate a midpoint Riemann sum. Well, if you think about the word midpoint, there has to be something in the middle because we have to take the point that's in the middle. So when I draw my subintervals here, notice that it says it wants 3 of them. The subintervals need to have something in the middle. So I start at 0, I work over until I have something in the middle, which means I would stop at 8.8. Then I start back at 8.8, make sure that something gets caught in the middle there, which means I stop at 12.8. Then from 12.8 to 14.5 so that I can catch something in the middle. So what we're going to be using are these values right here that are in the middle of these subintervals. Okay, so this 1 over 6, we'll talk about what that 1 over 6 is here in a minute. Integral from 0 to 6 of c of t dt is approximately, I'm going to go ahead and put the 1 over 6 there. Okay, and then for the first subinterval, we're going to use the midpoint, which is 5.3, multiplied by the width of the subinterval. Well, the width of that subinterval is 2. Plus, go to the next subinterval. That would be from 2 to 4. We're going to, again, use the one that I highlighted, the one that's in the middle, 11.2. And then multiply by the width of the subinterval, which is, again, 2, since it goes from 2 to 4. And then plus, the last subinterval is from 4 to 6. We're going to use that number that's in the middle for the y value, so 13.8 multiplied by 2. And if you put that to the calculator, you're going to get 10.1. And now what it wants us to do is to use correct units and explain the meaning of this integral in the context of the problem. So this 1 over 6 that's in the front turns this into what's called an average value problem. And so what I want you to always remember is that whenever you see that fraction in front of an integral, that's talking about average value. So this is the average value, and it's the average value of the function that you are integrating. So again, we're integrating c of t, which if you look back up here, is the amount of coffee in the cup. And so this is the average value of amount of coffee in the cup. And let's see what unit that's going to be in. That's going to be in ounces from t equals 0 to t equals 6, and we're talking about minutes as far as time goes. Okay, so there's the midpoint sum. We just did the trapezoidal sum and the problem up there, so let me know if you guys have any questions on that. Okay, well, what if I don't want to approximate the area under the curve, but I want to find the exact area? Okay, well, I can do that. It's just going to take a lot of rectangles. Okay, so here's what I want you to kind of see, and I'm going to try to make this as clear as possible here. So let's see if I can draw a function that looks like this, and I want to find the exact area under this curve. And no, it's not a circle, so I can't just use the circle formula. Okay, well, if I take a couple of subintervals here, and I'm going to use a different color. I'm going to use green to start off. Then let's just say that I do a right Riemann sum, just for kicks here. So if I do a right Riemann sum, then that's going to be here to here, and then from here over, and then from here over, and then from basically no rectangle here since the y value is 0. So there's our approximation. Obviously not a very good approximation. Okay, well, what happens if we increase? Let's just see if we can double the number of subintervals. So let's go here, here, here. Okay, so let's double them up and see what happens. So now I'm going to, again, take the right endpoint. Okay, so the right endpoint is here, 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 and then here, and then here, and here, and also there. Okay, so hopefully what you've noticed now is that my red is a much better approximation than my green is. Okay, so the green was catching a lot of area that was outside of the curve and missing a lot of the area that was inside of the curve, and my red did a much better job. Now let's see if I can maybe try a different color here, maybe like an orange, if that will show up. Okay, so if I try an orange and I try to double them again, so I go here, here, in between all of these, okay, then what you're going to notice is that I'm going to get much closer to the actual area. So I'm doing these triangles, or these rectangles, sorry, okay, basically in the middle of all of these. Okay, and so what you can notice is that as I take more and more and more rectangles, I'm getting a better approximation of the area under that curve. And so the idea, and it sounds a little silly, and maybe you're like, well, how can we do that? But what we're going to do is we're going to take an infinite number of rectangles. Okay, well, what we're going to do then is we're going to add all of them together. So remember, in pre-cal, whenever we want to add a bunch of things together, we use this sigma symbol. Okay, and I wrote it down there for a reason because I'm going to write something in front of it here in just a second. So what I'm going to do is I'm going to start from k equals to 1, and then I'm going to basically just multiply by add up the areas of the rectangle. So the areas of the rectangle are going to be the function values, because all of these heights are function values, and we're going to be plugging in a plus k delta x, and then the width of all of these rectangles is whatever delta x is. So we're going to multiply by delta x. Now, if I want to take infinitely many rectangles, we're going to put n right there, and then we're going to take the limit as n goes to infinity. Okay, so this pretty much just needs to be memorized. These are really not hard problems. Okay, it's just basically identifying what exactly it is that you need, and basically just plugging it into the formula. And I'm also going to write in here that delta x, the formula for delta x is b minus a over n. Okay, so example 5, write the following definite integral as the limit of a Riemann sum. So the first thing I want to figure out is, what is delta x? Well, delta x is b minus a over n. So if I look here, b is 3 and a is 1. So this is going to be 3 minus 1 over n, which is 2 divided by n. So that's my delta x. Now if I want to write the following, the definite integral as a limit, I need to have a limit statement. So the limit as n goes to infinity of the summation from k equals 1 to n of f of a plus k delta x. Well, let's first of all figure out what a plus k delta x is. So I'm going to do some scratch work over here on the side. Well, a was given as 1, so I'm going to write that down, plus k times delta x, which was 2 over n, which is really just 1 plus 2k over n. Okay, well, what the formula says here is that we do f of a plus k delta x, where f is the function that we are integrating. So in this case, we're integrating x to the 4th. And so f of a plus k delta x is just going to be what we found for a plus k delta x raised to the 4th power. So 1 plus 2k over n raised to the 4th. Okay, so now I'm ready to just plug that into my formula here. So f of a plus k delta x is going to be 1 plus 2k over n to the 4th multiplied by delta x, and delta x was 2 over n. Okay, so there's my final answer right there. Now the reason I'm doing this problem on the summer assignment, okay, you might be like, well, that was a really hard question. I'm not really sure why you would put that on the summer assignment and expect us to try and do that by ourselves. Well, okay, it's not really by yourself because you have the video, but also this was probably the hardest multiple choice question on the exam, on one of our practice exams, and so I want you to get an early look at it so that when we do it in class, it doesn't seem as foreign to you when we do it there. Please let me know if you have any questions. I'll be more than happy to help you. You just have to let me know. All right, talk to you guys later for Lecture 7.